Hello, thanks for joining GG413 Geological Data Analysis. I'm Garrett Apuzen-Ito, and the topic of this series of videos is on hypothesis testing. Specifically, we'll look at various parametric hypothesis tests. But before we get into that, I'd like to cover some very basic concepts about the normal probability distribution and its use in making inferences about the population means. And this is section 1.5.14 of Wessel's notes. And two key concepts I'm going to cover also include confidence intervals as well as significance levels. So our main goal here is we're going to sample a population, and from those samples, we want to learn something about the mean of the population. We want to make an estimate of that mean, and as well as its uncertainties. So let's sketch a population distribution, and this is applicable for any population distribution. It can be normal, it need not be normal, it can be any population distribution. So I'm drawing so this is the population, PDF, and on the x-axis is the values of x. Now, as you recall, so let's sample this population distribution, and as we do so, let's see. So we may make a sampling here that has a mean located there and a standard deviation noted by the bars. So this is x bar 1 plus and minus S1. We may sample it and get a slightly different value of X bar and the associated standard deviation and so forth. Sorry, I got myself writing a bit small here. Okay, and recall from the central limit theorem is that as we sample from this population, the mean of our sample means will form a normal distribution approximately centered on the population mean. Okay, so we would say we could estimate mu is about equal to, say, the grand mean of our in this case our 3 samples plus and minus the standard deviation of our sample means. Okay, so that would be a logical way of estimating mu plus and minus its uncertainty. So given that X bar follows a normal distribution, and that's true for large N, I should qualify that. For large sample sizes, and that's, say, greater than 30. So given that our sample means follow normal distribution, we know that plus and minus 1 standard deviation of our sample means, so plus and minus Sx bar encompasses about 68% of all possible values of X bar, and that also includes the population mean. So how do we know that? Well, if we write, let's write, oops, what's wrong with my pen? Let's write some measure of x bar is equal to the mean of the grand mean of all our samples plus and minus s, the standard deviation of our sample means. And we'll write that as normalized values. And we're going to use z, and that's equal to x double bar plus and minus the standard deviation of the sample means minus mu over sx bar. And if the grand mean is about equal to mu, we can see that z is about equal to 1. So if we return to our normal distribution, and here we'll sketch the normal distribution in terms of the normalized value z. We know that values of z equals plus 1 and minus 1 encompass about 68% of all the possibilities. So by making our estimate of mu, defining our estimate as of mu as our grand mean plus and minus a standard deviation of the sample means, this, if we use one standard deviation to define our uncertainty, this gives the 68% confidence interval on mu. And so that's what defines the confidence interval. Again, 68% of all possible values of mu fall within this range. Now, we could we could be a little bit more conservative or be a little bit safer, and we could define, we could estimate that mu is equal to x, our grand mean, plus and minus 2 times the standard deviation of our sample means. And this would correspond to the 2 standard deviations corresponds to z equals 2. And that would give a confidence interval of about 95%. So this gives us, with this estimate, we're even more confident. We're not, we have a probability of 95% of encompassing the true mean, okay, but perhaps the potential disadvantage of estimating mu using 2 standard deviations is we lose a little bit of precision. Okay, so by increasing our uncertainty to be more confident that we're encompassing the values of mu, we're losing a little bit of precision about where mu precisely is. Okay, so in general, the 1 minus alpha confidence interval is bound by plus and minus z sub alpha divided by 2. And that's, of course, in terms of normalized values. So again, if we were to sketch out our normal distribution, and we wanted to define a confidence interval of 1 minus alpha, we would do that by finding the values of z that give that confidence interval. So in this situation, alpha is equal to the significance level and it describes the area to the left of minus z sub alpha over 2 and plus the area to the right of z sub alpha over 2. So each of these blue areas has an area of alpha over 2 representing the cumulative probability of values within the two tails, and the confidence interval is 1 minus alpha, and this is the area between those two z values. Okay, that's to write that out so you can have it in your note. So in the above example, when 1 minus alpha is equal to 68%, alpha is equal to 32%, and so z of 16% is equal to plus and minus z of 16% is equal to plus and minus 1. So in general, we would estimate mu as equal to the grand mean of all of our samples plus and minus z alpha over 2 times our estimate of the standard deviation of our sample means. Okay, and that gives the alpha confidence interval on our estimate for mu.